Hello again to the project Amor, ICME Awardis multimedia online resources. After having presented the cognitive vision of mathematics, I return in this module at long last to the original theme to which this series of talk is devoted, the learning of mathematics. In the last few modules, I presented a cognitive answer to the auxiliary question of what mathematics is. Much earlier, in module 2, I responded in cognitive terms to another preliminary question of what learning is. It is now time to put these two things together while tackling the original query, the one of the learning of mathematics. To refresh your memory, here is what I said in module 2 about learning. Inspired by the school of thought called participationist, I suggested that it would be useful to think about learning as a process of changing patterned ways of doing things, of modifying those forms of action that repeat themselves over and over again. As we know, these recurrent ways of doing things can be called routines. These are therefore networks of routines that constitute the object of learning-induced change. We develop such routine networks or specific activities to cater to our different needs, such as the need for food, for staying healthy, for saving energy, for recording our ideas, for solving problems, and so on. The critical characteristic of human learning is that its outcomes disclose cross-individual regularities. To say it simpler, for most common task situations we encounter in our daily lives as members of our society, we all tend to develop similar routines. We can thus speak about historically established activities that we all perform in particular types of task situations. The cross-individual uniformity of human actions results from the fact that we learn from one another. Moreover, the existing patterns of acting are being handed over from one generation to the next one and are possibly modified on the way. Mathematics, defined in this unit as a kind of discourse in which we tell stories on mathematical objects, is a case of such historically established activity. Therefore, learning mathematics can be defined as a process of changing the activity known as mathematical, and this may include changes in the mathematical vocabulary, visual mediators, routines, and of course, in the collection of mathematical objects and the stories about them that we tell and endorse. It is now essential to distinguish between two planes or scales at which such changes can be observed over time. According to our definition of learning, not only individuals, but also society as a whole can be said to learn mathematics. Learning at the individual ontogenetic plane is a process of individualizing an existing historically established activity. Here, individualizing means becoming a skillful participant in this activity. At the societal historical plane, learning means the act of bringing the activity into being in the first place, and then modifying it over and over again from one human generation to another. Individual learning is what is supposed to happen in schools, where societal learning is what researchers and developers try to attain in their laboratories and workshops. Of course, neither schooling nor research and development are the only ways to spur the respective forms of learning. Still, these two institutionalized activities are unique in their being fully dedicated to enriching and improving our individual and collective forms of acting. This unity of individual and societal learning is yet another manifestation of the non-dualist nature of the cognitive approach to all things human. According to the traditional dualist approach, learning and historical development involve changes in very different objects. Learning is defined as a change in the elusive entities called mental structures, whereas historical development means a publicly investigable evolution of the ways people act and the stories they tell. In contrast, within our current non-dualist approach, these two processes involve changes in entities of the same kind, human activities. Of course, since the process of inventing an activity for the first time is quite different from that of learning this activity from others, these two types of learning should not be expected to occur in the same way. Still, as erecting a house cannot begin from the roof, so the communicational activity cannot happen in an arbitrary manner. Some constraints inherent to the activity and its structure are likely common to individual and societal learning. In this module, I will deal with learning on the societal historical plane. The individual ontogenetic learning of the kind we find in schools will be left for the last module. While concentrating on the historical development of mathematics, I will briefly address three questions. How does development happen? Why does it happen? And what is it that makes this development possible? How does learning happen? Learning mathematics, whether individual or societal, may involve two types of discursive change. Since mathematics has been described as a storytelling activity, its learning may be seen as an effort to extend the collection of potentially useful stories about mathematical objects. Yet, as has been made clear in the previous modules, adding new stories does not exhaust the types of learning-generated changes. In the course of mathematical storytelling, a new type of object may occasionally emerge. It may therefore be useful to distinguish here between two levels of learning. The first type of learning, whether this learning is individual or societal, is the one that leads to an expansion of the theory of stories of all the existing objects. This is, for instance, what happened in history after negative integers had been grudgingly accepted and used as useful, and mathematicians, already quite proficient in manipulating these special numbers, had to investigate their properties and their relations to other mathematical objects. Quite a different type of development happens when a new kind of mathematical object is introduced. This time, not just the theory, but also the rules of the game, thus the whole discourse may eventually change. Think, for instance, about what happened in history with the first appearance of the negative numbers, that is, with the transition to the discourse of signed numbers. I will elaborate on this point, but first, let me introduce some terminology. These two types of learning can be called respectively object level and meta level. The first of these two types of learning seems pretty straightforward. It only requires systematic exploration of the existing objects. The new narratives about these objects seem to be dictated by logic. The existence of qualitatively different meta-level learning, on the other hand, is not even suspected by those who espouse the dualist vision of mathematics. According to the traditional outlook, developing mathematics is only about adding stories on the independently existing mathematical universe. According to the cognitive view, it is about creating and occasionally changing this universe in the first place. Meta-level learning is much more intricate and requires decisions that, rather than being logically inevitable, are a matter of choosing from among several options. Let me elaborate. We may now distinguish between four types of learning, differing from one another along the two dimensions, scale and level of discursive development. As I already said, this module is devoted to societal historical development, the one presented in the left column of the table. Within this column, I shall now concentrate on the more interesting case of meta-level change. I will return here to the example of negative numbers. With their arrival, a rather dramatic change in the rules of endorsement took place. So far, mathematical narratives have been considered endorsable when, as in physics, they appeared to constitute a reliable, precise reflection of the state of affairs in the world. In other words, They were regarded as laws of nature. Thus, 2 plus 2 appeared to be 4 because our experience has taught us that 4 things are what you receive whenever you put together 2 pairs of objects. Now, to fully accept the idea of negative number, there was the need to give up the real-world criterion and to decide that consistency with formerly endorsed narratives is all that is needed for the endorsement of the new one. Further, in the case of numbers, the meta-level development affected the use of certain words. For instance, the very word number had now a different extension and could no longer be considered as the name of a category of words that answer the questions of how many there are or how much there are. Finally, and most surprisingly, the new discourse gave rise to endorsed narratives that seemed to conflict directly with the existing theory. Thus, for instance, mathematicians now endorse the claim that a pair of non-equal numbers can be found such that their inverses preserve the order of magnitude of the original numbers. Think, for instance, about 3 that is greater than -5, and so is 1/3 in relation to -1/5. Due to all these changes, and especially the last one, we say that meta-level learning often results in the transition to discourse that is incommensurable with the one that has been practiced so far. It must be stressed that despite this rather radical change, mathematicians did not renounce all that they have known so far, but now they knew it somehow differently. Let me add a few explanations about the idea of incommensurability. I will begin with the notion of incommensurable stories. Here is one such example. Look closely at what is happening here. You are likely to say that the 2 stories endorsed by these 2 folks, this is 6 and this is 9, respectively, are incompatible. Yet, I prefer to say that these 2 narratives are incommensurable with one another. What is the difference between incompatible and incommensurable, you may wonder? Incompatible stories are those that cannot be true or endorsed simultaneously. These stories are subject to the Aristotelian law of non-contradiction. Of 2 narratives, A and not A, one and only one must be true. Incommensurable stories, on the other hand, do not obey the law of non-contradiction simply because, as the term incommensurability indicates, there is no common measure with which to decide about their endorsability, about their being true. To put it in the words of American philosopher Richard Rorty, who continued the work of another American philosopher, Thomas Kuhn, stories are incommensurable if there are no rules with which will tell us how rational agreement can be reached where statements seem to conflict. The discourses that produce such stories, incommensurable stories, will also be called incommensurable. Now we can say that these 2 stories here are incommensurable rather than incompatible. They use the same symbol, the digit written on the ground, in different ways, and are thus taken from different discourses. Each of the stories is true or endorsable in its discourse and does not exclude the other one. 2 immediate vital conclusions from here follow. First, the property of being endorsable or true is no longer absolute. Narratives are true or not within the discourse in which they have been created, but not beyond it. This also means that the law of non-contradiction obliges within a discourse, but is not applicable in between discourses. Second, the incommensurability of discourses is difficult to see, if only because incommensurable discourses may feature the same words. This creates a risk not unlike that of an invisible hole in the pavement. While unaware of a discursive gap between your interlocutor and yourself, you may stumble upon it, maybe even fall into it. More specifically, you may think that your disagreement with your partner is about facts, while in fact, in reality, you are talking about something different than he is. The resulting debate may go on forever, never reaching any conclusion. If we put all this together, we see that meta-level learning, which often results in a discourse incommensurable with its predecessor, is a complex matter. Throughout history, it spurred many long-lasting controversies, and it requires a special care in the classroom. I will return to this subject in the next unit. For now, let me give some thought to the question of why societal learning happens in the first place. I have just noted how difficult this kind of learning may be, especially if it is to happen at the meta level. To overcome this kind of difficulty, or even just to be ready to grapple with it, we must be motivated by prospects of no less than dramatic gains. And indeed, recall that while defining mathematics as storytelling, I said we engage in this particular discursive activity because of the usefulness of mathematical stories as tools for sense-making and for mediating our practical activities. It may therefore be our constant wish to enhance our practical activities that drives the relentless historical development of mathematics and fuels our efforts to teach mathematics to practically every young member of our society. While it is certainly not the only factor behind our propensity for the learning of mathematics, it is undoubtedly the most central one. Thus, to answer the question I just asked, I must take a closer look at the growth-generating relation between mathematical storytelling and how we provide for our practical, everyday needs. Before I do this, I have to be clear about the distinction between these two types of activity. Mathematical activity, which includes such actions as calculating, proving, corroborating, and establishing scientific laws, aims at enhancing theories of mathematical objects, and as such may also be described as discursive or theoretical. The other routines, those to be called practical, and this includes cooking, building bridges, and riding bicycles, for example, aim at manipulating and transforming objects or relations between objects rather than just describing them. I will now argue that mathematical and practical activities spur each other's development. To show what I have in mind, I will use an example. I will present the hypothetical scenario for how the numerical discourse might have first emerged and then repeatedly grow over time. Whereas admittedly quite speculative, this script will shed light on the basic mechanism that, with high probability, seems to be at work when a new or enhanced mathematical discourses are coming into being. Let us start with the following historical question. Where could the discourse of numbers possibly begin? To answer, we should probably first address another query. Let us think about elementary practical activities that we perform daily, activities with which even the very young child may already be familiar, if only in the restricted version of these activities. Which of these daily activities, possibly practiced in one form or another from the dawn of humanity, cannot be performed without the discourse on numbers? That is, in the beginning, it was performed without the discourse of numbers, but then it grew and could not be performed without numbers any longer. I suggest that at this point, you pause the video and think about it for a minute or two. Are you back with me? If so, I believe some of you might have already arrived at the same conclusion as I have. The relevant activity that has been probably known from earliest times is that of comparing two sets with regard to their size, or what will later be known as their cardinality. In the beginning, this could be done without counting, just by arranging both sets physically into one-to-one correspondence. Yet, comparing two sets in this way stops being feasible if the sets are not simultaneously present or when they are too numerous to be manipulated in this way. And now, let me tell you the resulting story of numerical discourse and its development in some detail. It may appear somewhat speculative, but and not more than a conjecture, but I hope you find it reasonable. My point of departure is the assumption that the historical reason for the invention of numbers was our ancestors' desire to extend set comparisons beyond situations in which the small sets to be compared are simultaneously present. It is in response to this need that the device that could mediate such mapping, that is counting, has been introduced. After a while, the appetite of our forefathers and foremothers grew again. Why only sets, they said to themselves, why not continuous objects that can be compared along their different dimensions, such as length? So far, it was possible to compare lengths that were simultaneously present, but not those that were too distant in space or time, or too big for that matter. So our predecessors invented the talk about ratios, which are pairs of natural numbers, also known as fractions. I could continue this story presenting account of further developments in the discourse of numbers. Yet, I will cut it short because our time is obviously not limitless. Hopefully, you've got the gist of the story. I can generalize what you have seen here as follows. Our practical and discursive activities are co-constitutive. We develop discourses that help us enhance existing practices. And we develop forms of life that the new discourses afford. These two types of activities pull one another and induce each other's development, just like the movement of forward of one leg entails the movement forward of the other. Having just made my point, I now must add a disclaimer. Not every mathematical discourse is close enough to familiar practices to be built directly from our everyday deeds. At the later stage, new mathematical discourses will be developed out of existing ones. Thus, for instance, elementary algebra taught in schools might have originally emerged from explorations of arithmetic relations between numbers. If so, it is simply a formalized meta-arithmetic. And another example, the idea of the rational number might have popped up in response to clear parallels, not to say isomorphisms, between several types of talk, that on parts of a whole, that on points on number line, and that on ratios. The discourse of rational numbers became a unifying meta-discourse of all these and some other ones as well. Considering these later examples, one concludes that mathematics develops by annexing its own meta-discourses. As such, this development is practically unbounded. What fuels this never-ending growth? Well, our insatiable desire to be able to say even more with even less, to incessantly create ever more powerful generalizations, to climb to ever higher levels so as to arrive at ever wider, indeed breathtakingly broad views, or just to explore whatever is out there for no other reason than the fact that it is there. While doing all this, we also believe that the resulting mathematics will prove one day to be a powerful enhancer of our practical activities. From what I just said, it follows that both our practical and mathematical activities incessantly spur each other's development, adding one layer of complexity upon another. In other words, our societal historical learning, whether discursive, mathematical, or practical, can go on forever, and there are no constraints on the resulting complexity. The last question that I will ask now is, what is it that gives us this capacity for the for practically unbounded accumulation of complexity? Or in more general words, what is it that makes the ongoing societal historical learning possible? In response, I will now claim that we have two intimately interrelated types of repositories of complexity. The first of them are the physical tools that we use in our practical activities. The others are discourses that mediate those activities, among them mathematical discourse with its unique squeezing capacity. Now, to convince you about what I just said, I need to answer a new question. How do tools and discourses accumulate complexity? Let me begin with the tools. We are as keen on building ever new tools as we are on developing our discourses. It is mainly the mechanism of successive compression that makes this unceasing expansion possible. Here is how it works. First, we construct a new tool, and it may be quite sizable, as was the first computer presented here. We then compress that tool, sometimes achieving truly impressive results, as was the case with putting this first mammoth machine on a single chip. We then use this new miniature tool as a building block for new, much more powerful ones. Our capacity for constructing and then storing ever new tools is thus attained in cycles of construction, compression, and then building a new tool around the resulting miniature version. The compression in this case is attained in what is known as the process of miniaturization. And now to the role of discourses in accumulating complexity. You can see here the mechanism of periodic compression, not unlike the one that works for physical tools. In the case of mathematical discourse, the cycle may begin with a story of some mathematical operations. For instance, the one related to extracting the square root, as presented here. The story will be compressed by reifying root extraction into a new mathematical object, in this case, into the square root function. We can now start building new stories around the one about the square root function. This time, the compression has been attained thanks to well-known already the discursive procedure of objectification. To sum up, our activities grow ever more complex thanks to periodic compression of tools and then building new tools around them, and also thanks to periodic objectification of discourses and building new discourses around them. Okay, one remark is in order here. In spite of this relentless growth in complexity, we do not experience a proportional growth in the effort that must be invested in the use of tools or in the participation in discourses. This is because of the fact that with every increase in complexity, much of what needed to be done at the previous level of complexity is turned into a black box, into the miniature version of the former tool, all into a new noun replacing a long processual description. None of these black boxes needs to be opened to be useful. Thus, at any stage, we deal only with the latest layer of complexity. I am happy to be able to wrap up this module with a powerful conclusion. I just made clear that societal learning, whether discursive or practical, is the one thing that makes humans special, that sets us apart from all other species. Discourses seem to play the primary role in the historical transformation of human forms of life, because apart from their own capacity for accumulating complexity, they are also indispensable for the unbounded development of tools. Indeed, can you imagine an emergence of computers, bridges, or spacecrafts without the mediation of intricate stories afforded by our discourses at large and by the mathematical discourse in particular? If so, this may well be our early developed capacity for the unique forms of communication that bears main responsibility for the fact that some time ago, some of our prehistorical ancestors hit the fast track to humanness. If all this is true, it would not be exaggerated to say that as humans, we are, in a sense, the product of our discourses, mathematical discourse not the least important among them. Okay, this would be all for today. To learn about how individuals become participants of historically established mathematical discourses and how this process may be influenced by different factors, please proceed to Module 8 of my unit on cognition. Thank you.